Assalamualaikum and hi everyone. For trends in periodicity in 3.2, we are going to discuss the atomic and ionic radius, the trends in ionization energy and electronegativity. But in this video, we are going to focus on atomic radius. In this video, we are going to discuss the variation of atomic radius across periods 2 and 3, across the first row of transition element and down a group. Enjoy your learning! Before we discuss more on the variations of the atomic radius across a period and going down a group, let us see on how to measure the radius of an atom. The radius or size of an atom is difficult to be defined exactly because the electron cloud has no clear boundary, meaning that we cannot simply measure the size of an atom starting from this end and to this end. This is because in one atom, we don't have any clear or distinct orbital. Okay, we just have electron cloud. To solve this, the atomic radius is taken as half of the distance between the nuclei of two adjacent identical atoms. So for example, we have atom A and the other identical atom A. So in order to know the atomic radius of this one atom, we will take from this one nuclei to the other nuclei in the next atom. So by doing that, we can identify the radius of an atom. In order to discuss the variations of the atomic and ionic radius in the periodic table, we will use these two major factors. They are effective nuclear charge ZEV and shielding effect or screening effect. So ini adalah dua major factor yang kita akan guna pakai dalam membincangkan tentang perubahan size of atom and ion in this chapter. But for ionic radius, we will discuss in the next video. The first factor is effective nuclear charge ZEV. So ZEV is a net positive charge experienced by valence electron due to nucleus attraction. Dalam bahasa yang mudah, kita boleh kata bahawa ZEV ini adalah some sort of attraction forces daya tarikan yang dirasai oleh valence electron disebabkan oleh tarikan nukleus. ZEV can cause valence electrons and valence shell to be pulled closer to the nucleus. So let's have this nitrogen atom as the example. So from the electronic configurations of the nitrogen, we have 1s2, 2s2 and 2p3. So from what you have learned in the previous lesson, you can identify the valence shell from this electronic configuration. So here we will have 2s2, 2p3 as the valence shell and 1s2 as the core or inner shell. So electrons in this valence shell are called valence electrons, and the electrons in the inner shell is called inner electrons. So from this orbital of nitrogen, we can find out that this will be the valence shell, okay, that having 5 electrons, and orbital inside here will be the inner shell. So what ZEV can do? ZEV can cause the valence electrons and valence shell to be pulled closer to the nucleus. So maksudnya di sini adalah ZEV ini akan menyebabkan valence shell di luar ini dan juga valence electron tertarik ke dalam, ke arah nukleus. So ini yang akan menyebabkan shrinking of the atomic radius. So efek ini hanya berlaku kepada valence electron yang berada pada valence shell sahaja. As the effective nuclear charge increases, atomic size will be decreases. Effective nuclear charge is the net positive charge. So apabila effective nuclear charge bertambah, bermaksud apabila nilainya menjadi semakin positif, atomic size will be decreases. So to know how to calculate the value of the effective nuclear charge, you can use this formula. That is ZEV equals to Z minus S. Z is the proton number of the element and S is the number of electrons in inner orbitals. So in the case of nitrogen atom, to calculate its ZEV, it is Z minus S. Z is the proton number 2 is the number of inner electrons in the inner orbital. So here is the inner orbital or inner shell. So we have 2 electrons here. So this 2 value will be put here. The answer of ZeV value for nitrogen is plus 5. So again, the greater the positive value, meaning that the greater the effective nuclear charge, the atomic size will be decreases or smaller. So this is one of the factors that affecting the atomic and ionic radius. Second factor will be shielding effect or screening effect, kuasa perisai ataupun kuasa pelindung. So shielding effect will shield valence electron from nucleus attraction. So kalau dalam ZeV tadi, ZeV adalah berkenaan tentang attraction forces between the nucleus and valence electron. Okay, tapi dalam shielding effect, it is all about melindungi valence electron from nucleus attraction. Melindungi valence electron daripada tarikan nucleus. So this shielding effect is caused by the inner shell electrons. So do you still remember which are the inner shell electrons? So here we have the valence shell. Orbital inside is inner or core shell. So from here, electrons outside here will be the valence electron. And electron in the inner orbital or shell are inner electrons. Shielding effect exists due to the repulsion between the inner shell electrons and the outer electrons. Electrons in the inner shell shields outer electrons greater than electron in the same shell. So, bagaimanakah the presence of these inner electrons can shield the valence electron from the attraction of the nucleus? Caranya adalah dengan mewujudkan repulsion between the inner shell electrons and the outer electrons. So apabila elektron inner bertemu dengan elektron ataupun menghampiri dengan valence electron di sini, so apa yang wujud between them? There will be repulsion forces. So why repulsion force? Kenapa repulsion yang akan exist between them? Because we have electron E minus bertemu juga dengan electron E minus. Okay, charge yang sama. So bila charge yang sama ni dekat antara satu sama lain, maka they will repel with each other. So electron in the inner shell akan repel dengan electrons in the outer shell. So this kind of repulsion akan membuatkan or menjadikan valence electron dan juga valence orbital ini expand keluar. Okay, menjauhi the nucleus. So apabila kedudukan valence electron and valence shell jauh daripada nucleus, maka daya tarikan between these two akan menjadi kurang ataupun lemah. So in this case, in the case of shielding effect, electrons in the inner shell will shield outer electrons better than the electron in the same outer shell. Maksudnya, kuasa perisai ini adalah lebih tinggi, lebih baik dilakukan oleh elektron pada inner shell berbanding dengan elektron yang berada pada shell yang sama. So that's why shielding effect or screening effect also can affect the atomic and ionic radius. By looking at this image, you can see clearly the difference between effective nuclear charge ZeV and shielding effect. So here we have outer electrons or valence electrons in the valence shell, and electrons at the inner core, here we call it as inner or core electrons. So the attraction between this valence electron towards the nucleus, this is so-called ZeV, that is effective nuclear charge. Daya tarikan di antara valence electron dan nucleus kita panggil sebagai effective nuclear charge, ZeV. Meanwhile, the repulsion forces between the core electron and the valence electron here yang kita panggil sebagai shielding effect. So, since effective nuclear charge ZeV adalah berkenaan tentang tarikan di antara nucleus dan valence electron, so we can say that the greater the value of ZeV, lagi kuatlah valence electron ini akan tertarik ke arah nucleus, dan ini akan menyebabkan size of the atom will be smaller or decreases. Berbeza dengan shielding effect disebabkan oleh inner electrons. So these inner electrons akan shield, akan melindungi attraction forces between the valence electron and the nucleus. So bila ada sahaja pelindung, maka valence electron is said to be less attracted to the nucleus. So ini yang akan menyebabkan size of the atom will be increases ataupun getting bigger. So shielding effect akan menyebabkan atomic size getting bigger and ZEV akan menyebabkan atomic size getting smaller. Across the period, from left to the right, atomic size will be decreases. So you can see from the image as well, from the sodium to chlorine, the size of the sodium to chlorine will be decreases. So kenapa jadi macam ni? Let's see the explanation. These are the elements of the period tree. So as we go across the period, you can see that the atomic radius is decreases. And we can see also the proton number increases from sodium to chlorine. What is the relationship between the proton number and atomic size? So across period, from left to right in the periodic table, as the proton number increases, effective nuclear charge ZEV will be increases, attraction between nucleus and valence electron increases, atomic size decreases or getting smaller. So when the proton number increases, effective nuclear charge ZEV will be increases. So what does it mean by effective nuclear charge ZEV increases? So let's recall what you have learned in the factor of ZEV before. ZEV increases meaning that its value becoming more positive from sodium to chlorine. This will cause the attraction between the nucleus and the valence shell and valence electron will be even greater. Okay, lebih kuat. Tarikan di antara nukleus terhadap valence electron dan juga valence shell akan menjadi lebih kuat. So bila tarikan antara kedua-dua tu kuat, apa yang akan jadi? Valence electron and valence orbital will be pulled closer to the nucleus. Maka akan berlakulah contraction of the radius. Okay, contraction of the atomic size. So when ZEV increases, attraction between the nucleus and valence electron will be increases, so the atomic size will be decreases. So this is the reason kenapa when we go across the period, atomic size will be decreases. It has something to do with ZEV. So to prove the value of ZEV increases from the sodium to chlorine across the period tree, you can calculate the value of their ZEV respectively. To calculate the value of ZEV, ZEV equals to Z minus S, di mana Z is the proton number and S is the inner electrons in the inner shell. So in this case, you must know the electronic configuration for each one of them dahulu, and then you can find the inner electrons, how many inner electrons, and from there you can get the value of ZEV. So from the calculation, we find out that the value of ZEV for sodium is +1, magnesium +2, +3, +4, +5, +6, and +7. So these are the value of ZEV for the respective elements. As the proton number increases, the value of ZEV increases. So the attraction between the valence electron and valence shell towards the nucleus will be increases. So hence that will cause the atomic radius of Cl will be the smallest among the elements in the period tree. Sodium and chlorine both are located in the same period, that is period 3. So both of them will have the same amount of principal quantum number, that is n equals to 3. From their electronic configuration, for sodium 3s1 is the valence shell and 3s2, 3p5 are the valence shell for chlorine. Meanwhile, these configurations will be considered as inner shell for sodium, and these configurations will be inner shell for chlorine. So, by knowing the number of inner electrons in this inner shell, then you can calculate the ZEV for sodium. So, the value of ZEV for sodium is +1. Compared to the ZeV value of the chlorine, since chlorine has 10 inner electrons, so ZeV value of chlorine will be +7. So we can see from these two values, even though they are located in the same period with the same principal quantum number, but ZeV for sodium is smaller than ZeV of chlorine. Jadi, apabila value ZeV of chlorine lebih positif berbanding dengan ZeV of sodium, ini akan menyebabkan valence electron of chlorine dan juga valence shell akan lebih tertarik ke dalam menghampiri nukleus dan mendekati nukleus. So, tarikan yang kuat menghampiri nukleus ini akan menyebabkan atomic radius of chlorine
decreases and the size is smaller than sodium.
So this is the reason why atomic radius of chlorine is the smallest for elements across period 3. So now, let us see the variation in atomic radius across d block elements. That is for transition metals. So as what we have done for period 3 elements just now, you can see across period 3, the atomic size will gradually decreases. Okay, perubahan of atomic size untuk elements across period 3 itu adalah agak ketara, daripada besar menjadi kecil. And for period 4 elements as well, we can see that these elements are decreases in their size as we go across the period from left to the right of the period 4. But what happens to the atomic size of the transition elements in the middle of the periodic table? If you can see from these atomic size values, we can see that the atomic radius of transition metal across the period are not much changes. Size of the transition element across period tidak menunjukkan perubahan yang begitu ketara.
Meaning that the size of the transition metal atoms across the period adalah lebih kurang sama.
And as you can see from the graph as well, exception to scandium and titanium, kita abaikan scandium dan juga titanium. So from vanadium to zinc, we can see that there are not much changes in their atomic size. Okay, perubahannya macam so-so saja, lebih kurang saja. Kenapa ni boleh jadi untuk transition metal, sedangkan ini adalah case across the period? Sepatutnya kalau across the period, surely proton number will be increases. So bila proton number increases, and surely the ZeV should be increases. But when ZeV increases, how does the ZeV does not give effect towards the atomic size of the transition metals? So let's check out the answer. Here are the value of atomic radius in picometer for transition metals in period 4. So let's abaikan scandium and titanium and let's focus on vanadium until zinc. So from these values of atomic radius, we can see that there are not really much changes, okay, in terms of the atomic radius between them. So size, atomic size untuk transition elements in period 4 ini adalah lebih kurang sama, okay, tidak banyak perubahan. Okay, berbanding dengan elements-elements lain untuk period 4. So, kenapa ini boleh terjadi? In the first row of D block elements, except scandium and titanium, 3D electrons shield the 4s electrons in outermost shell more effectively from the nuclear charge. 4s will be less attracted to the nucleus. Maksudnya adalah, kita ambil contoh vanadium. So this is the valence electronic configuration untuk vanadium, 4s2, 3d3. Kenapa? Sebab kita isi elektron pada 4s dahulu, and then the balance of the electron kita isi pada 3d. So after you have filled with electrons, later you have to change the position between 4s and 3d. So awak akan dapat the new configuration of the valence will be. Jadi ini adalah valence electron configuration untuk vanadium. So di sini antara dua ni kita akan kata 4s ini akan terletak pada outermost shell. Okay, they are valence shell. Tetapi yang paling luar outermost adalah 4s2. Okay, kerana 3D ini terletak sedikit ke dalam daripada 4s. So di sini apabila 3D ini letaknya di sebelah dalam, maka this 3D and other inner electrons yang lain akan shield these 4s electrons more effectively daripada attraction of the nucleus.
According to Aufbau principle, whether in chromium, manganese, ferrum, cobalt, nickel, copper dan zinc, semua elektron akan diisi pada 4s dahulu dan selebihnya akan diisi ke dalam 3D. So di sini kita akan nampak penambahan of elektron pada d orbitals in this transition metals atom. Apabila elektron pada 3D bertambah daripada vanadium sehingga ke zinc, so ini menunjukkan bahawa elektrons pada 3D orbitals akan shield 4s electron more effectively from the nucleus attraction.
So hence, apabila 3D ini akan berfungsi untuk melindungi 4s daripada tarikan of the nucleus, so shielding effect will be increases. The screening effect by inner electrons cancel the increased value of nuclear charge across the period. So all transition elements experience roughly similar force of attraction to the nucleus across the d block elements. Maksudnya di sini adalah bila kita go across the period, of course proton number akan bertambah. So apabila proton number bertambah, ZEF juga akan bertambah. Tetapi dengan kehadiran shielding effect by the inner shell electrons, shielding effect ini akan cancel ZEF. So apabila ZEF telah pun di-cancel oleh shielding effect, so all elements in this periodic table akan experience roughly similar force of attraction to the nucleus walaupun proton numbernya bertambah daripada kiri ke kanan. So atomic size do not change very much for the first row of the D block, okay, which is for transition metals. Perubahan size of atom untuk transition metals pada period 4 ini adalah okay, lebih kurang sama. Tidak banyak perubahan pada atomic size mereka. Exception for zinc, 3D orbital is completely occupied with electrons, causing more effective shielding effect by the inner electrons and increase in mutual electron-electron repulsion in the outer shell. So as you can see in the value of zinc here, okay, di penghujung of susunan of transition metal in period 4, tiba-tiba value atomic size of zinc ini meningkat sedikit. Okay, so what is the reason? So puncanya adalah disebabkan oleh dua faktor ini, iaitu shielding effect by inner electrons, itu yang pertama, dan yang kedua adalah mutual electron-electron repulsion in the outer shell. Bermaksud mutual electron-electron repulsion di dalam valence shell.
In this image, you can see that since zinc has many electrons than the nickel, so zinc will have more effective shielding effect and also increases in their mutual electron-electron repulsion, okay, disebabkan oleh d orbitals are completely occupied.
Now, let us discuss the variation in atomic radius down a group. So, going down any group in the periodic table, the atomic size will be increases. Menuruni any kumpulan di dalam periodic table, size of the atom akan semakin besar. How could this happen? This is because, as the principal quantum number increases, shielding or screening effect will be increases as the number of inner electrons increases. So attraction between nucleus and outer electron will be decreases. Valence electron will be less pulled inwards by the nucleus, so atomic size will be increases. Again, apabila principal quantum number n increases, so number of electrons di dalam inner orbital akan semakin bertambah. So ini akan menjadikan shielding effect akan semakin bertambah. So bila shielding effect bertambah, inner electron akan melindungi outer electron dengan lebih efektif. So dengan itu, attraction between nucleus and outer electron or valence electron will be decreases. Okay, itu akan menjadikan valence electron kurang tertarik ke arah nucleus dan ini akan menjadikan atomic size will be increases. To understand better what happened going down the group, let us see this diagram. So here we have elements of group 1, lithium and sodium. Lithium is located in period 2 and sodium is located in period 3. And both of them are coming from the same group, that is group 1. Kenapa group 1? Sebab mereka ada satu valence electron. So the difference between lithium and sodium adalah lithium ada satu inner orbital and sodium ada dua inner orbital. So in this case, kita akan boleh expect bahawa jumlah inner elektron di dalam sodium melebihi jumlah inner elektron di dalam lithium. Since sodium has many inner electrons in inner orbitals, so these inner electrons will shield the valence electron from the nucleus attraction more effectively. So the shielding effect caused by this inner electron in sodium is even greater than the shielding effect in the lithium. Shielding effect yang kuat ini juga akan menyebabkan valence electron akan kurang tertarik kepada nukleus. Hence, valence electron and valence orbital akan lebih expand ke arah luar menjauhi nukleus.
This should explain why atomic size getting bigger as going down a group.
And how about the ZEF? Adakah ZEF memainkan peranan untuk case going down the group? So let us calculate the ZEF for lithium and sodium. So first, you need to identify the inner shell of lithium and sodium. So these are the inner shell of them. So next, by using the formula of ZEF, which is Z minus inner electrons, you can find the value of ZEF for lithium and sodium. So here, the value of ZEF for lithium and sodium are constant. So ZEF did not give any effect for the case going down the group. As the conclusion, across the period, atomic radii decreases due to the increase of effective nuclear charge ZEF. So for the case across the period, ZEF will be the main factor affecting the atomic size. For the case down the group, atomic radii increases due to increase in principal quantum number n and shielding effect. So for the case down the group, shielding effect will be the main factor.